Hello class, this will be the first video in a series of videos. We'll start with 3.6 on chain rule, then we'll do a little bit of 3.7 with the exponential rule and the logarithmic rule. Okay, we will start with chain rule. Chain rule is quite important because we're going to be dealing with some functions. Like for example, in the beginning of this chapter, we talk about the sine of x squared function. And so this is a function composition. Our f of x is just the sine function, sine of x. Our g of x is that inside function right here, which is x squared. And so really the thing that we're taking the derivative of is f of g of x. And so in this composition, with the regular rules we have, like power rule or the derivative rules for trig functions, we don't have any way of really handling sine of x squared. And that's really what this rule will enable us to do, and it'll just increase the number of things that we can do the derivative for. Now, I want to take notice right here of this first derivative. And so as I defined it here, f prime is going to be the derivative of your outside function. So in the example to the right, that is sine x. We want to take its derivative. So this right here is the derivative of the outside function, evaluated though at the inside function. I write the word evaluated here. At, and I'm just going to call it g of x, but we're really talking about the inside function. And so this interior for the derivative is the same as the interior for the original function. So in other words, when I take the derivative of sine, I'm going to evaluate it at x squared. I'm not going to change that. A lot of students will do g prime in the inside. So they will do, they know the derivative of sine is cosine, but instead of evaluating it at x squared, they'll change it to 2x because they want to take that derivative. But the chain rule says, no, keep it exactly the same, so we know we're going to get cos of x squared, which is the same as what we started with. The second part for chain rule, and this is the most important part in the sense that most students forget this more often than not, is when we look at g prime, this is the derivative of that inside function. Okay, of the inside g of x. And so this is like an adjustment factor. That's kind of the phrasing that I used earlier this class when we talked about chain rule with the derivation, which is on the previous page. But when we talk about the derivative of this inside function, we're adjusting how the behavior of just f alone works by a multiplier determined by that inside. So we know that it can't just be cos of x squared, because that would be mirroring how the derivative of just sine x works, and it should be moving faster because x squared moves faster than x does. And so we multiply by this adjustment factor, and that adjustment factor is the derivative of your inside function. In this case, that's the derivative of x squared. You should by now know how to take the derivative of x squared. That is 2x, and then we have cos of x squared, okay? And so that is the outside derivative evaluated at the inside function, and then the inside derivative. We multiply them together. Some textbooks and some teachers really do like this formulation where we substitute in for the inside function. Usually we use the label u. This is to match some later techniques in integration where we do what's called u substitution. But really, this is all the same thing. Our u is g of x, and that means that du dx is g prime of x, the same as above, okay? So in this case, this is the inside derivative again, okay? And then in this case, because u is g of x, then our function y is just f of u, or in other words, if we use that example on the right, that would be sine u. And so when I do dy du, I'm really just doing f prime of u, okay? And so this right here is just the derivative of the inside, or excuse me, derivative of the outside. And so this is just a second formulation. Some students really like this formulation because it behaves a lot like a fraction. You could imagine if this was a fraction, we could cross out these du's and we would recover dy dx. And so this is a really good technique for inserting. It kind of visually represents this insertion of this middleman that we're using. So u is just this middleman reference to the inside function g of x. And it is more useful the more complicated these derivatives get. And if you take Calc 3, we do have to use this more. I'll kind of be sticking more so to the first definition up here, though, for future reference. That's kind of my preference when I teach this. So let's come down, and we will do the example below. And so, oh, actually, I did the example to the right. So this work right here is the same work that would go in that example, okay? I'm going to go ahead and bring that down. I already did it. Go. And so we have, we get 2x times cos of x squared. That would be the result for sine of x squared, okay? And so let's go to the next page where we can talk about a different example. Okay. So let me just make up an example here. So let's say that y is equal to, let's do something simple. We'll do a polynomial, like let's do 1/2 x plus 2 to the 10th power. Okay, so presumably you could do this derivative in the normal way. If you really wanted to, you could do the algebra, right? And you could just expand this thing, and you could multiply this out 10 times. And hypothetically, by doing that, you could get this down to be a polynomial, and then you could take the derivative the normal way. But I imagine most of you don't want to do this algebra. It would take quite a while to expand this 10 times, get a huge polynomial. So there's a better way. We'll use chain rule. Okay. So my outside function, f of x, is the rule that says, hey, I'm going to take the 10th power. My inside function is this 1/2 x plus 2. Okay. And so the derivative of the outside function is we're going to bring the 10 down, and then we're going to subtract 1 from it. Whereas the derivative of the inside function is just going to be 1/2, right? Because the derivative of x is 1, the derivative of 2 is 0. So putting this all together, if I want to find y prime, when I take this derivative of 1/2 x plus 2, the 10, I take that outside derivative just like I did above. And so I'm going to get 10 times something to the 9th power. And that something stays the same from the original problem. Right here, I have 1/2 x plus 2. So on my result, I'll have 1/2 x plus 2. Don't change the inside at all. Then I need to multiply by my adjustment term. That adjustment term is the derivative of that inside. That is the derivative with respect to x of 1/2 x plus 2. Well, we already did that derivative. We know that that's 1/2, right? And so our final answer should look like 10 times 1/2 times 1/2 x plus 2 to the 9th power. A half times 10 is 5. So really, we're going to write this as 5 times 1/2 x plus 2 all to the 9th power. You cannot simplify that further. Like, we can't pass the 5 in or anything like that because of that 9th power. So we'll just leave it like that. Okay. And this thing that we're doing here, where we're doing the power rule, but we have kind of something inside the power rule, this thing is common enough that it gets its own rule. And so that's what this example here is really doing, is we're deriving what's called the generalized power rule. And this works if you have any function g of x to some power. So like if I have sine to the 5th, or in the previous example, 1/2 x plus 2 to the 10th, anything where I have some function to some power, we just apply chain rule. So if I want to do y prime, I'm going to take the derivative with respect to x of g of x, the nth power. And so power rule says, hey, bring the n down and then leave the inside alone. Okay, so chain rule says, again, take the derivative of the outside function like that. Don't change the inside. So still g of x. I've not done anything there. But chain rule says, okay, well, now that you've completed the outside derivative, you have to multiply by the adjustment term, which is the derivative of that inside function. What is the derivative of the inside? Well, we don't know what g is, so we'll just call it g prime, right? That's just a placeholder. Once we know what g is, we can find g prime, and we can put both those answers in. So putting it together, we have a generalized power rule where if I take the derivative of g of x to the n, that's always going to equal n times g of x to the n minus 1 times g prime of x, okay? Now, really commonly, this formula is given in terms of u instead of g of x because that's a little more compact. So a lot of times you will see it with u to the n, and this will give us n u to the n minus 1, and then we'll multiply by du dx. Whatever u is, we're going to take its derivative. And so this is basically just a case where u is equal to g of x, and some people prefer this really compact notation instead of getting mired in like what g of x is. Okay, now that's basically the same formula that I have written here in both ways. And so you guys can reference them here or my own handwriting. Either way is fine. So you do not need to memorize these rules. If you prefer to just use chain rule, you can just use chain rule. But some students really like to just have a technique or a rule that they can apply universally. So if you're one of those students, you have that rule for you. Okay. Let's do another example. We have a 100th power here. So certainly at this stage, when we have a power this big, you're never going to do the algebra any longer. It's just not feasible. Like a 100th power would take you days potentially to expand algebraically before you took your derivative. So we're going to use that generalized power rule. So when I take the derivative with respect to x, this is my y prime of the quantity x cubed minus 1 to the 100th power. I'm going to bring the 100 down, right? And then I have x cubed minus 1, the original g of x, to the 99th power. And I'm going to multiply that by d dx, the derivative of that inside x cubed minus 1. Okay? X cubed minus 1, that's really going to become, so when we do this derivative, we bring the 3 down, so then we subtract 1. So this is 100 times x cubed minus 1 to the 99. And this, we bring the 3 down, 3x to the 3 minus 1 plus 0, right? The derivative of 1 is 0. And so we want to go ahead and put all that together. The 3 is going to multiply by the 100, so we're going to get 300. I'm going to bring this coefficient, this x to the front. And so when you bring that forward, we're going to write it 3 minus 1 is 2, so this is going to be x squared. And then we have x cubed minus 1, the 99. Okay? Like this. I'll do a couple more just to make sure that you guys are kind of getting a sense for how this goes. So let's do y is equal to the sine. Actually, you know what? Let's do it this way. Let's say that I have sine to the 10 of x. Okay. So you may not at first glance realize that this is a generalized power rule, but remember that when we write the number there, we're really saying that this is a 10th power of sine of x. So it may be easier to tell by writing it like this. Okay. But really, when we're doing this, we're talking about the 10th power of sine of x. Okay. And how do we do that? Well, we use the generalized power rule again. We take the 10, bring it down, we leave the sign alone, and we change the power to a 9, and then we multiply by our adjustment factor. That is the derivative of my inside function, which is sine of x. Okay. What is the derivative of sine? You guys should be studying this. This is one of the rules I expect you guys to know. But for now, I can tell you for sure, the derivative of sine is cosine, positive. And so we're going to end up with sine to the 9th of x. Okay. I'm just going to go ahead and write this back, kind of like we wrote it originally. Bring the 9 back down. And so our final answer is 10 cos x times sine of x to the 9th power. Okay. Or sine to the 9th of x. Either way you want to write that. And so you get something like this. I will do one more, which is this one down here with the square root. And so you need to remember that with square root functions that we need to rewrite, or in fact, I should say any roots, you need to rewrite as a power. So how do we do that? If you guys recall, if you take the nth root of x, you can always write that as x to the 1 over n power. Okay, so we write it as a fractional power. So for f of x, we're going to write this as 1 over x squared plus 4, the 1/2 power instead of square root. Now, that's still not enough because power rule does not apply to things in the denominator. It only applies to things in the numerator. So remember that, again, I'll use u this time again. When we're using power rule, this is not the same as the derivative with respect to x of 1 over u to the n. Like, that's very different. You can't just assume because you have a power, you can apply power rule. It must be a power in the numerator, okay? So we need to bring this up, and we're going to write x squared plus 4 the negative 1/2, like that. Okay. Now f prime of x will do as normal. I'll bring the negative 1/2 down. Negative 1/2. I leave the inside absolutely alone. I don't do anything to it yet. We're not ready for that, right? So then I take negative 1/2 and I subtract 1 from it. And I need my adjustment term. Okay, what do I adjust by? I always just take the derivative of that inside function. This is my g of x or my u, whichever framing you prefer. but we're going to take the derivative of that inside function, x squared plus 4. Need to clean this up. So I have negative 1/2 times derivative of x squared plus 4 is 2x. Okay, that's just, we bring the 2 down, subtract 1 from it, derivative of 4 is 0. We get negative 1/2 times 2x. And then we still have x squared plus 4 to the power of, we need to resolve this. You have negative 1/2 minus 1. You're going to go and you're going to do 2 over 2 instead of 1 because you have negative 1/2. I don't know why I wrote that as negative 1. We have negative 1/2 minus 1, so that's really negative 1/2 minus 2 over 2. We're going to get 3/2 negative. Negative 3/2. That. The 1/2 and the 2 are going to cancel out here. And so our final answer will look like negative x all over. I'm going to go ahead and move it down. X squared plus 4 to the 3/2. No reason to write it as a root. We'll just write it as 3/2, but that is our final answer here. Okay, using chain rule. And so the chain rule is really contributing this minus x term. If you didn't do chain rule, you would just end up with 1 over x squared plus 4 to the 3/2. And so that's a typical answer I'll see when people don't really know chain rule because they just know how to do the square root part, but they don't actually know how to handle the x squared plus 4. And so this one is missing that that minus x part. Okay. Well, actually, I should say there would be a minus 1 here. The minus is not coming from the chain rule. The minus is coming from the minus 1/2. In fact, I think you would actually get, if you did this without chain rule at all, you would actually get negative 1/2 like this. And then maybe you move the 2 down and do some other work, but that's not going to be sufficient, okay? Got to make sure that you guys are doing your chain rules. We have some more complicated ones. So I will do one more, and this is going to basically integrate. We're going to have a quotient rule now. You guys can all see that this is a fraction inside of my power. And so when I do my chain rule, I'm going to get a quotient rule out of this. Okay, so let's try it. We're going to do ddt of t minus 2 over 2t plus 1, 15th power. And I apply my outside derivative as normal. So my outside derivative, when I use power rule, says, hey, bring the power down. I'm going to leave the inside totally alone. I don't change anything to it. And then I'm going to subtract 1 from it. Okay. Do not stop here, though. This is not the final answer because I have to then multiply by my adjustment term. What is my adjustment term? That is ddt, in this case, of my interior t minus 2 over 2t plus 1. This is itself a quotient rule. So we're going to get to the stage where you're going to have a chain rule inside of a quotient rule, or like this case, you have a quotient rule inside of a chain rule. That's normal. We're going to start layering these techniques, product rule, quotient rule, all of that comes together, okay? So let's do this quotient rule. I'm going to go ahead and stop here for a moment, and I'm just going to do this quotient rule to the side. And then we'll find out what this is equal to, and we'll bring it all the way back to the top again and put it into this as a solution, okay? So when you do quotient rule, we have f of t on top, that is t minus 2. We have g of t on bottom, that is 2t plus 1. And then we'll do the derivatives. F prime of t is 1, and g prime of t is 2. And so when we set up our product rule, we'll do this cross multiplication. We'll take f prime times g, and we'll take f times g prime. And I'll make sure I keep the order consistent with the way I've drawn these arrows so that I make sure that when I do the subtraction in the middle, it's in the right order, okay? I want to make sure I'm taking the derivative of the top function first and the derivative of the bottom function second. Don't forget, when you do quotient rule, you must divide by the denominator squared. This is 2t plus 1 all squared. So putting that all together, we have 2t plus 1 minus 2t plus 4. Okay, remember to distribute the minus sign and distribute the 2. And all over 2t plus 1 squared. 2 t's are going to cancel. 4 plus 1 is 5, so this is 5 over 2t plus 1 squared. And so we can bring this up as a solution to that part of this equation. And so I'm going to have 15 times t minus 2 over 2t plus 1 to the 14th power times 5 over 2t plus 1 all squared. Okay, we could clean this up a little bit. You may want to separate this fraction so that it's 15 times t minus 2 to the 14 times 5 over 2t plus 1 to the 14 times 2t plus 1 squared. Okay. And so that's going to give us a final answer. Let me adjust. I wrote too large one more time. I do this to myself too often. I'm going to go ahead and slide this product rule back at its little pocket over here. Sorry, quotient rule, excuse me. And that way I can finish this problem without it interfering. So we'll put this up in here. And so finally, 15 times 5 is 75. T minus 2 to the 14 all over. I have 2t plus 1 to the 14 and 2t plus 1 to the second. I'll add 2t plus 1. 14 plus 2 is 16. Okay, so that would be the final answer. If you stopped here, that would I wouldn't be too upset about you stopping here, though I would multiply the 15 and the 5 and get the 75 at the very least. But if you're in a time crunch under an exam conditions, I would wait to do any finishing algebra on this style of problem until you know you have excess time at the end of the exam. Okay, so I would stop there and then maybe put a mark and come back to it later. Okay. All right, so we'll stop after example 40 for this video. I'll go ahead and stop it, and then I'll do a couple more examples in another video that'll be optional. Those will be the slightly more complicated ones with like multiple layers. But I don't want to run this one super long, so let's do one more. In this case, we're doing f double prime, so we're gonna have to be careful. That is the second derivative, okay? Not the first, we want the second. The first will be our first step, but we're gonna need the second at the end. I'm not gonna belabor this. When we do f prime of x, we take the derivative of sine of x, which is gonna be cosine of x. But again, it's not x, it's x squared plus 1. And then we multiply by the derivative of the inside. That is x squared plus 1. So my f prime, my first derivative, is 2x cos of x squared plus 1. Okay. Now, when I do my second derivative, I'm going to take a derivative of the result I just got. And when I do that, I'm going to get a product rule. Okay, so I have 2x cos of x squared plus 1. And this right here is a product rule. Okay, because I have 2x times cos of x squared plus 1. And so don't forget your other rules. Just because we're doing chain rule doesn't mean product rule can't come back. So let's go ahead and start doing that. I'm going to go ahead and put this in the edge here a little bit. Zoom us back in. And so when we do our product rule, I'm going to not do all the setup. If you'd like, you could definitely do like f of x equals 2x and g of x equals cos. But I'm just going to do this straight jumping to the result. Okay, so I'm going to take the derivative of the first, which is 2x, times the second, which is cos x squared plus 1, plus the first, which is 2x, times the derivative of the second. That is the derivative of cos of x squared plus 1. Okay, I'm just jumping straight to the setup of product rule. The derivative of 2x is 2. So we're going to get 2 times cos x squared plus 1, plus I have 2x times the derivative of cos x squared plus 1. Well, the derivative of cos is negative sine of x. And so we're going to do negative sine of x squared plus 1. The inside. Don't change the inside. Remember this, every stage of chain rule, the inside of that trig function is staying the same the whole time. I've not changed it at any stage. And no matter how many derivatives I do, it will never change, okay? But I do have to multiply by the adjustment term again. And if you are recalling from our earlier derivative, that's going to be 2x, the same as before, right? Just like it was 2x over here. So we'll put this together. I'm going to have 2 cos of x squared plus 1 plus, well, this is 2x and this is 2x, so I'm going to get 4x squared. And then I have a minus sign from the sign, so I'm going to go ahead and take this plus and switch it to a minus, and then we'll put our sign here. Okay, and so this is the second derivative of f. Just like that. Okay. Alrighty, that takes care of chain rule at a basic level. So this will get you through, I would say, 60-70% of the homework. And then if you want to come back and watch the other video, which will be Okay, let's spice it up. Let's do more than one chain rule. Let's do a quotient rule with a chain rule inside it, or maybe it's a product rule with two chain rules. Okay, so we will do more of these examples in the next video. You're welcome to try some of the homework though, get a feeling for the basics of chain rule, and then return to do the more complicated ones. Okay, so let's put a pin in that, and then definitely check out the next video when you feel like you're ready after some practice. Okay.